Thank you. Thanks so much. I'm delighted to be back. Jeff and Rod, thanks again for the invitation. For me, 2 years ago, this is where I took my first steps into the low-carb community, and I've enjoyed it. As you probably know, I don't attend or present at many of these kinds of meetings. It's because I'm a father of young kids, and being with them and giving my wife a break is priority number one, but here I am. So you're my next priority this time. I am delighted to be here. I'm glad to follow Zoe in particular because most of you are too polite to get up and leave and you all wanted to hear her. Now it's time for me. Again, thanks for being here. I'm delighted to be invited. In a way, I'm coming back to what I started with 2 years ago. Not in a way, I am. And so let's just get started. In the end, I'm going to impress upon you how ketones are eliciting such a unique change in mitochondria across two distinct cell types, overall creating what I would consider to be a metabolic advantage. Here are my disclosures involved in educating and supplementing. Now, let's get into it. Last time, 2 years ago, when I presented, I didn't mention these academic ancestors that were really a motivation and inspiration to me, in particular, Elliot Joslin. But Joslin and Benedict, a diabetes and a metabolism scientist, came together to ask the question, to what degree is metabolism or metabolic rate changed from healthy versus type 1 diabetics? And please note the year. This was before insulin was used as a therapy in type 1 diabetes. What they found was that the people with type 1 diabetes had significantly higher metabolic rates. This one finding started me asking the questions that I presented 2 years ago, and I'm now following up and showing you kind of the data to finish the story. It started with them. Since then, I've found more data that supports this general paradigm that insulin is relevant for metabolic health. In particular, 70 years after Joslin and Benedict's study, Sri Nair, while studying in the UK, published this paper in type 1 diabetics. So first of all, let's note that they noticed type 1 diabetics had a higher than expected metabolic rate. Based on their body size, which is the main driver of metabolic rate, they had a metabolic rate that was about 300 calories per day higher than it should have been. Interestingly, when they gave them insulin, the metabolic rate dropped to where they expected. It went down about 300 calories per day. In the end, it was a difference in metabolic rate of around 15 or more %. So insulin, this hormone that many of us implicate in being causal or at least very meaningful and significant with adipocyte size and obesity by extension, is having an obvious effect on metabolism or mitochondrial function. And moreover, they detected this very rapidly. In real time, they found when they administered the insulin to the type 1 diabetics, within just minutes, they could start to detect this reduction in metabolic rate. Insulin was slowing things down. Now, there's a lot more they looked at. It's actually a very neat paper. And there's the reference if you're curious. So all of this was floating in my mind 2 years ago when I presented my very first low-carb community talk, which again is so delightful. It is uncommon for a scientist to get up in front of people and have them clap with enthusiasm. Usually it's 20 other scientists who don't really care. They just want to make sure, they just don't want you to get the next funding that they're trying to get. Nevertheless, I presented this paradigm where obesity could be explained by either purely caloric accounting or rather a balance of hormones promoting catabolic or anabolic processes. While both of these are certainly relevant, the laws of thermodynamics need to be considered. What I submitted to you was that the endocrine theory actually encompasses and accounts for the caloric theory, insofar as when the main anabolic obesity-promoting hormone insulin is down, the body has entered such a state that beta oxidation of the fats, and I'll come back to this in a bit, is so high that we now have ketogenesis. And ketones are creating this particularly unique metabolic milieu where the cells of the body are more inclined to just spend energy. in the form of increased metabolic rate and in the form of wasting. Remember, anytime you're detecting ketones in your breath or in your urine, those ketones are little pieces of fat that otherwise would have had to be accounted for, and now they've simply left the body. So it's slight, that's not a lot of calories, but it nevertheless needs to be considered, and I don't believe it always is. Nevertheless, this was the general conclusion 2 years ago with a little bit of preliminary data to support it. Now, we'll finish the story, pretty much, so I probably won't ever talk about this stuff again. Now, let's look at the body. So within all of us, we are interested in metabolic rate, and in a way, metabolic rate represents a fire, it's a flame. It is giving life, animation, and even, yes, heat to our warm-blooded bodies. This heat, this little fire, is the consequence of multiple reactions, countless reactions happening in the body. And all of these chemical reactions can be lumped into one of two general processes. They are either promoting the growth of molecules, using energy to grow things, those are the anabolic reactions, or it's taking these big molecules and breaking them down and getting energy from it to do something else. So the catabolic reactions. At its purest definition, this is metabolism, despite the way even I may sometimes use the term. If we're talking about metabolism, we are, strictly speaking, talking about the sum of all anabolic and all catabolic reactions. Now, if there's a fire in our bodies, this metabolic fire, how do we fuel the fire? Well, that, of course, comes from the foods we eat, our 3 macronutrients. Now, I'm presenting these up here as if they're all equal when it comes to fuel, but they are not, as you know. Carbohydrate and fat are, in fact, fuel. Protein, I think it is not justified to consider protein a fuel because it is only used as a fuel very acutely, as David Ludwig showed earlier, in transition on a low-carbohydrate diet or even fasting, assuming the person has enough fat to rely on for the production of ketones, or in true end-stage starvation. Otherwise, protein is minuscule when it comes to its contribution to energy. So we will look at protein as a builder, and thus we won't consider it, I'm not going to consider it fuel, so let's just drop it. Despite it being very important, we're going to stick with fuel for now. And we're looking at the whole body, but in order to talk about metabolic function, we have to zoom in a little bit, and of course we come to the so-called powerhouse of the cell, and that's the mitochondria. So the mitochondria are the organelles within the cell that are taking fuel with a little help from oxygen, because in a way, this kind of is like a combustion event. It is burning these nutrients. We have to have oxygen. And now, in the presence of oxygen, the mitochondria are they're catabolizing these nutrients, this nutrient energy. In the process, as a result of any chemical reaction, we always get a little bit of heat. So I'm going to denote that, and I'll come back to that idea. But the mitochondria are better than a normal campfire. They aren't just producing heat. They're clever enough to actually get something productive out of it. And that productive thing that I want you to keep in mind is the production of a molecule called ATP. You've likely heard of it, but just to create a common definition for the sake of my talk, ATP represents cellular or chemical currency. We often say that. We professors teaching our undergraduate students. And because I've missed class all week, you're my undergraduates for today. It's not an insult, I hope. But nevertheless, the ATP is what the cell actually uses to get work done. It will use ATP, for example, to relax the muscle. When the muscle is contracting and relaxing, that's a phenomenon known as cross-bridge cycling at the microscopic level, and we need ATP to do that. Neurons in the brain and nervous system will use ATP to maintain the appropriate shifting or flux of electrolytes for the sake of conducting an impulse across the length of a neuron, and many, many more things. Suffice it to say, the cell will use ATP to get something done, which I'm just going to define right here as work. So the production of ATP represents a cell being productive. Now, with all this in mind, let's shift the paradigm a little bit to enable me to present another concept. So the mitochondria is interested or are interested in producing ATP, this evidence of it being productive and earning its keep within the cell, if you will. This, of course, requires fuel. And so we'll bring up again fat and carbohydrate and the relevance of oxygen in these points throughout these reactions. And then the mitochondria will catabolize the nutrient energy, producing the chemical energy. Normally, or on occasion, this will happen in what we could consider an ideal balance or an ideal ratio. In other words, the mitochondria are only using as much nutrient energy in the form of fat and carbohydrate as is needed to produce the chemical energy in the form of ATP. So essentially, we would say it's happening at a 1-to-1 ratio. It's only using as much energy as it needs. Now, here's the first important point. In this state, we would consider the mitochondria as being coupled. Now, this isn't some honeymoon advice. I mean, again, we're taking the chemical energy, and it is tightly coupled to how much nutrient energy is only being used to the degree that the cell or the mitochondria is producing ATP, this chemical, workable, functional energy that the cell can use to get some work done. So we'll say that's happening in a coupled state in this arbitrarily set 1-to-1 ratio. Oh, and of course, in the process, it's so efficient that there's relatively little heat. In other words, and I'm just mentioning heat as a sign of waste, because heat is evidence of a chemical inefficiency at the level of the chemical reaction. Now, let's shift it a little bit. In this same paradigm, we could have the mitochondria working in such a way that it's using relatively too much carbohydrate and fat, and it's getting relatively less ATP being produced. Of course, that nutrient energy that's being catabolized, if it's not being yoked or coupled to the production of ATP, it's going to be producing more waste in the form of, say, an exaggerated heat emission from the chemical reaction. But in this case, because we're using relatively more nutrient and getting relatively less ATP, we've uncoupled that process. The cell is using more energy than it actually needs. And so again, uncoupled would be the state in this relative imbalance where we're using more nutrient energy than we're producing chemical energy. So to wrap this general point up, let's superimpose the two concepts. The mitochondria are using nutrient energy in either a very coupled way, in other words, it is yoked to the production of ATP, it's somewhat demand-driven, it's only using as much as it needs, or the mitochondria are being very wasteful, and they're using more nutrient energy than needed for the sake of chemical energy. So to put it another way, and very explicitly, in a coupled state, the mitochondria are using energy very sparingly, or very efficiently. In an uncoupled state, it is inefficient, and it's using the energy quite liberally. All right. Now, because I teach undergraduates and my lectures are always 2 hours long, I have to find ways to keep the students engaged, and I'm constantly fighting with Facebook and Instagram. So that's all. Actually, I find that's a balance of a little bit of irreverent humor, a little like what Zoe utilized earlier with great finesse, but also with analogy. So here's my analogy. Let's look at the mitochondria as an engine. And because we don't feed an engine with carbohydrate and fat, we feed it with gasoline or diesel, which I'll just call fuel. And the engine doesn't produce ATP. It, of course, just produces work, which I'll convey with these gears because the engine is promoting it's moving gears, moving axles, moving wheels. And so those little axles will be evidence, or those gears will be evidence of the engine actually moving the car. Now, in my car, which is a 20-year-old 5-speed manual transmission Subaru Outback, I see the RPMs and the speed. And because I have a clutch, I can really readily control these two things. Anyone who drives a stick shift knows what I'm talking about. In fact, so few students drive it that when I park on campus, I don't even lock my doors. They couldn't steal it if they tried. They'd be pushing it. Anyway, so here's the general paradigm that I'll use to convey this idea. And then we'll come back, I promise, to the relevance of ketones. We are getting there. This is just my long-winded introduction, but hopefully for a point. So ideally, as I am pressing down on the gas pedal in my car, My foot is off the clutch now, I'm in gear, and I see a subsequent and relative increase in the speed of the car. In other words, as I'm pushing the fuel into the engine to be combusted, I'm getting work out of it. And so the gears are spinning, the axles are spinning, the wheels are going, and in other words, it's working very well, and I'm not wasting my fuel in the form of heat production. And so in this particular situation, where I'm just pressing on the gas and my other foot is off the clutch, we would say that the engine is only burning what it needs for me to start moving the car. Thus, in this state, where RPM and speed are relatively matched, the engine is coupled, if you will. Now, in contrast to the student who would try to steal my car, they don't know how to drive a stick shift, a manual transmission, so they're pressing on the gas pedal, and yet they don't know to lift their foot all the way off the clutch. They are riding the clutch, so to speak. And so the actual amount of speed or movement or work that the student is getting out of the engine is pretty low. The car's not really moving. And in this case, of course, as I'm indicating, there's not much work going on, but the fuel is still being used because they're pressing down on the gas pedal, and that's being manifest in this inefficient production of heat. So, in this case, the engine is using more energy or more fuel than it needs in order to get the work done. So the engine is uncoupled under the hands of this novice driver. Now, I'm not a car guy at all, despite my affection for my very old beat-up Subaru, which I plan on making my daughter's first car. So in this case, let's go back to the body. And because we're going back to the body, let's stop talking about fuel in a generic sense, and let's talk about one in particular, and that is fat. And again, let's just keep shifting the analogy back to being relevant, and so we'll drop the RPM and speed, and now we're going to talk about oxygen use as evidence of fuel use, the rate at which the mitochondria are working, because if mitochondria are working, they are using oxygen, and then we'll look at the production of ATP, the productive aspect of what the mitochondria are trying to do. Now, in this case, as you know, this audience knows better than most, if fat catabolism or fat use is very high for very long, we begin to produce these small little molecules called ketones. Interestingly, when someone is in active ketogenesis and thus ketosis, or getting to what we would define classically as ketosis, that production of ketones accounts for almost half of all of the oxidation of fats. So if someone's burning fat like gangbusters, so to speak, almost half of that is actually going to the production of ketones, a pretty meaningful amount. Of course, this can only happen when insulin is low. And in fact, that is what got me involved in ketones in the first place a few years ago. I'm an insulin guy at my core, but you can't really separate the ketones from the insulin. Well, nowadays we do with supplements, but those two things are inversely related. And of course, the gist of it, the biochemistry in a very simple way, is that as fat is low, the oxidation or the burning of, as insulin is low, the burning of fat is so high that you start to accumulate a lot of acetyl-CoA. And acetyl-CoA represents this very relevant kind of branch point in biochemistry where it can go all kinds of different ways. Because insulin is low, it cannot go to lipogenesis and be used to create fat. Also, because there's so much acetyl-CoA, it inhibits its own entry into the citrate cycle. I bet many of you are actually understanding everything I'm saying. And so I think you probably are. I don't mean that in a cheeky way. But it can't be catabolized in the citrate cycle, which means no gluconeogenesis and no more energy production. There's only one avenue left. And of course, that's ketogenesis. So, nevertheless, that was a bit of a tangent. Now, all of this has been introduction. Finally, you're thinking, Professor, let's get on with it. I will. So now let's look into the data that my lab has generated, where we've been exploring the effects of ketones on adipocyte mitochondria and muscle mitochondria, particularly skeletal muscle. Interestingly, we also recently have some incredible data from brain tissue, but I'm not going to show that this time. Maybe next time. It's just there's not enough time and too much to talk about. So let's talk about the muscle first. In the case of the muscle, I'm going to base these data on a paper we published from my lab last year, where we found, let's look at a few things, and I'm not going to show you all of it, although I would submit it's all quite relevant to this conversation. First of all, we found in figure A, we're just looking at the rate at which the muscle cells are using oxygen. And you'll see in the ketone-treated cells, the muscle cells are using a little more oxygen than normal. Not a lot, but it was significant. It's a slight increase in oxygen consumption. Very importantly, we also measured something called the respiratory control ratio. That's the figure at the bottom. That's a general indicator of mitochondrial fitness or health. In other words, how well are the mitochondria responding to what we're doing in a fashion that we're expecting? And what we see is that these mitochondria are actually a little more responsive. In other words, they're a little healthier based on this one particular metric. Also, this one's important. We see in figure D, ATP production is trending upwards. Importantly, and I'll come back to this when we get to the adipose data in a minute, in figure E, you'll see that the P to O ratio. This is an indicator of how much ATP is being produced per unit oxygen consumed. In other words, how efficient is it being, or, in other words, how coupled are the mitochondria? And we actually see that there's this upward trend, not statistically significant, but it's certainly not less. When the muscle cells were treated with ketones, there is at least a fully maintained coupled state. What's interesting, when we look at the bottom figures, the mitochondria are actually producing less what we could call exhaust. There's less H2O2 production, which is one of the main reactive oxygen species that are generated. So when people talk about oxidative stress, when anyone talks about the relevance of fats being oxidized and causing atherosclerosis, we actually more accurately say the fats are peroxidized because of what hydrogen peroxide is doing. So it's a very powerful, very relevant reactive oxygen species, and there's less of it when the muscle cells are fed ketones as a fuel. Now, the general conclusions then on this one particular section. What are ketones doing to muscle with regards to mitochondrial function and even a little beyond? Not much change in the rate at which it's using oxygen. The respiratory control ratio suggests a slight but significant increase in overall mitochondrial health. I didn't take the time to show you this, but we found also that ketone-fed muscle cells were more what we call viable. They grew better and were more resistant to injury. So they were a little more robust, a little tougher, if you will, which is a good thing for any cell and muscle cells in particular. They had reduced production of reactive oxygen species in the form of H2O2, that primary ROS molecule. And then lastly, we found a maintained and even a trend for increased ATP production. So if we look specifically at the from the perspective of the mitochondria, we see that it's using a lot of oxygen. The mitochondria are pressing down on the gas as readily as they want to, and they're getting a lot of activity out of it. It's working. So the mitochondria are as productive as you would expect as it is ramping up its use of fuel. So what that means, again, in this case, the mitochondria in the muscle cell, when fed ketones or exposed to ketones, are very well coupled. They are using the energy they need. And for a cell that has a high energetic need, and yet not a lot of storage in itself as energy, that is, I would submit to you, a pretty clever use of ketones, or a clever response to ketones, to be very efficient and prudent with the use of energy in a tissue that has such a high workload and demand and expectation, and yet so little actual energy stored. Of course, it can take in energy very readily. Now, is this relevant? I'll do this with the adipose data as well, but I submit that it is. This study from several years ago, looking at people in a ketogenic diet, found an increase in lean body mass, some of which, of course, was muscle. You aren't gaining muscle if muscle cells are wasting energy. As anyone knows, that anabolic reaction of building muscle mass is extremely expensive, energetically speaking. And moreover, this could be evidence not only of very well, tightly coupled mitochondria, but also the fact that the ketones, as I mentioned, we found are helping the muscle cells be a little more robust and resistant to injury. So this increase in lean body mass could also be a reflection of the muscle cells themselves simply being a little tougher than they were before. Another study published by preeminent ketone scientists in the UK, and you've all seen this study, they found that actual exercise production was better when the athletes were fed relatively less glucose and relatively more ketones. So again, a potential evidence suggesting a relevance to what I was showing you, that ketones are a good fuel for the mitochondria, perhaps because, or for the muscle cell, because of what the ketones are doing to the mitochondria, helping them work in a more tightly coupled state. In other words, using nutrient energy insofar as it needs chemical energy. Okay, now let's look, before we leave the muscle behind, let's look at the heart muscle, which for you right now, not me, because I'm up and I'm animated, for you, your heart is the main caloric demander when it comes to muscle. Of course, the liver and the brain are higher than the heart, but the heart is still very relevant with regards to muscle. This study, published a few years ago by some legends, Chuck Hopple in particular, being a heart mitochondria guy, they found that the failing heart, so in heart failure, the heart starts to rely more on ketones. A follow-up to this found that the failing heart, as it was relying more on ketones, actually increased its production of ATP. That's what that figure is showing. As the ketone had two levels of ketone in the heart failure situation, the attack, you could see that the ATP production went up as the ketones went up. And so the ketones at the heart are improving ATP production. It wasn't enough to rescue the heart failure in this model, but it still was sufficient. The ketones did increase ATP production. I believe that is, again, evidence of ketones helping the mitochondria be more tightly coupled. And again, that means using nutrient energy more efficiently in the production of chemical energy, ATP. All right, now let's leave the muscle behind and get into the fat cells. I need to admit or present this as well, that some of the same people from the UK ketone preeminent group found that ketones help brown fat be a little more uncoupled. That's the gist of this particular figure, and they were looking at uncoupling protein 1, or UCP1. Now, if this is kind of unfamiliar, brown fat, white fat, I'm not going to take the time to talk about it because I will assume that you are like my students and you've done your homework before coming. If it is new to you, then I beg your pardon, I'm not going to take the time, but Jeff and Rod posted my lecture from 2 years ago, and it's readily available on YouTube. So you could check that out for understanding the difference between brown fat and white fat. But very briefly, brown fat has a lot of mitochondria that are very uncoupled. White fat has very little mitochondria that are very tightly coupled, only using energy when it needs to. Okay, so this is just some background, showing that before I ever started talking about this, there were others who were talking about it, probably much more lucidly and with a much more beautiful accent. But by the way, the Canadian group, why are you ignoring one of your own? Just because I've lost my Canadian accent, man, I'm a little upset. I don't have a man without a home, I guess. All right. Anyway, so let's now look at the rodent work that we did, and then I'll move into the human work, making it supremely relevant, I promise. Here we were looking at white adipose tissue. The prototypical, in fact, the type, the fat on the rat and the mouse, it's the same. It's this small little pocket of subcutaneous fat. Rodents don't have a lot of subcutaneous fat like we do. And of course, there's an ethnic kind of disparity among humans. But generally, as people are getting fat, a lot of that is subcutaneous fat, which is generally pretty healthy. So I always joke with my students, if it jiggles, it's good. It might not look good, but it's healthier than the alternative. So briefly, what we see here, and we're looking at the white adipose tissue, WAT, the O2 flux, the amount of oxygen the adipose tissue is taking, you can see that in those bright blue bars, the ketone diet animals, their oxygen consumption was significantly higher. In other words, this white adipose tissue, that importantly has the capability to act a little bit more like brown adipose, what's called, it becomes beiged. It's not quite brown, but it's not quite white anymore. It's a little in the middle. It's behaving a little more in an uncoupled fashion. So the mitochondria are wasting energy more. And that's reflected in that observation. It's using significantly more oxygen. In other words, it's using its fuel much more readily. Importantly, we do not see a relative increase in ATP production. So that bottom figure really tells the story. The amount of ATP produced per unit oxygen consumed, the P to O ratio, drops significantly. Strong evidence that ketones are causing this white adipose tissue to become more uncoupled. And we see very relevant changes in gene expression that would be mediating, causing, in other words, these mitochondrial changes, increasing the number of mitochondria and the degree to which they are uncoupled. Now, in humans, what we've done, this is still unpublished, but getting more and more solid all the time, we have humans coming in two groups: weight stable, adhering to standard diet, and no detectable ketones from a blood ketone monitor, or in obvious ketosis detected and measured, quantified. We've done two things to these people. We measure resting energy expenditure under a metabolic, a little hood, like a space helmet they wear, and we just track the gas exchange with oxygen and CO2. That gives us something called, that's indirect calorimetry, which we're using as our marker of resting energy expenditure. And then we're also pulling fat biopsies from their bellies, the subcutaneous abdominal fat. So let's look at the adipose biopsy data first. We firstly see in this very condensed, simplified version of looking at oxygen use, a significant increase in the amount of oxygen consumed in the fat tissue of humans that are in ketosis. So very clear, definitive evidence that these mitochondria in these fat cells are more active. Now, when we look at the ATP production, in particular, the amount of ATP being produced per unit oxygen consumed, again, what we define as the P to O ratio, or how we measure the P to O ratio, it is almost half. So these mitochondria are half as coupled, or in other words, twice as uncoupled as the mitochondria are in the fat cells from the people eating the standard diet. In other words, the mitochondria in the fat cells of the people adhering to a ketogenic diet, people that are in ketosis, whose fat cells are seeing ketones, it is causing mitochondrial uncoupling. And we don't have the gene data yet, and that's on the way. Now, with resting energy expenditure, we did not detect a significant change in energy expenditure across our patients. However, when we split it up by age, we saw something. In fact, it was significant. There was a slight but significant increase in resting energy expenditure in the older subjects. And that's myself included, so I can use that term without offending anyone. So in the older subjects, compared to the younger college-aged in particular subjects, we saw the difference. Ketones were doing something in the older people at fat tissue that they weren't doing, or at whole body level, I should say, that wasn't obvious at the whole body level of the younger subjects. So in this case, as we conclude this section, we see that the ketones are dramatically increasing oxygen consumption in the mitochondria of fat cells, meaning the mitochondria are much more active. They're very healthy still. There's nothing clearly wrong with them. However, they are making much less ATP, definitive, undeniable evidence of the fact that these mitochondria are more uncoupled. So they're wasting energy. And then in the end, this increased degree of wasting energy in the form of just heat, this could explain the differences we see in resting energy expenditure. So in this case, the mitochondria in the fat cells with ketones, they are pushing the foot, they're pushing the gas pedal. So the oxygen consumption is ramped up. And there's not a relative increase in obvious work or productivity. And so these mitochondria are, as you of course know already, very uncoupled. Now, what's the relevance here? I submit again there is a lot of relevance. This study, published by people who don't like this kind of conversation, nevertheless provided pretty wonderful supporting evidence to find that in this extremely tightly controlled environment, people that were in ketosis, despite eating the exact same amount of calories, had a slight yet significant increase in metabolic rate. Another study, and Dave Ludwig showed these data earlier. Now, he would be the first to say in his study, these people were not in what would classically be defined as ketosis. But nevertheless, they found that in the group with the most tightly controlled carbohydrate consumption, or I should say least amount, they had the highest metabolic rate. Some degree of uncoupling may explain some of what we're seeing. And that may explain why people in a ketotic or a ketogenic diet, a ketotic state, don't have to try to account for calories quite as precisely as someone who's not in ketosis. There is obviously a little more wiggle room. And again, it could come down to the level of the mitochondria and whether the mitochondria are coupled or uncoupled. And in fact, very briefly, when I heard David Ludwig's talk this morning, and I consider this kind of a nice follow-up to his, I had mentioned 2 years ago data that I only showed a little bit, but when insulin is very high, ketones are low, of course, because of the inhibition of beta oxidation and the very powerful inhibition at every step of ketogenesis that insulin elicits. Ketones are wiped out. In this, we published a paper last year. We find that in animals, when we induce hyperinsulinemia, resting metabolic rate is down, particularly in the dark cycle, which is when they're more active because they're nocturnal. We see that when we look at these specific fat depots, perirenal, which is visceral white fat, subcutaneous, which is the fat that can shift into more beige-like, or the prototypical brown fat, which on the animal is interscapular, and on humans it's kind of all around the thoracic area. We see that those fat depots that can be a little more uncoupled became less uncoupled. In other words, more tightly coupled when insulin was elevated. So insulin was making brown fat, which wants to waste energy, or fat that can kind of behave like brown fat, act more like white fat. It was making it be more tightly coupled. In other words, wasting very little energy. And we supported this, or this finding was supported by biochemistry looking at actual protein levels. So in conclusion, the data find collectively that ketones are inducing a mitochondrial uncoupling in fat cells. The fat cells are using nutrient energy, but not really getting productive chemical energy out of it. So again, it has uncoupled those two processes. In contrast, ketones are actually maintaining, if not improving, the coupled status of the mitochondria in muscle cells. So one way to generally look at this in conclusion, and reflective of my love of alliteration and making sure my students can always remember some key point, ketones are inducing this state of affluent adipose tissue. In other words, it is wealthy and it is very liberal with the wealth. In contrast, it's inducing this state of miserly muscles. So the muscles are more reluctant to give away their energy. They're only using what they need. Altogether, I believe this creates a situation where ketones, given the different effects of the mitochondria in fat cells versus muscle cells, what we could consider a metabolic advantage. Thanks for listening. If you have any questions, I would look forward to getting them. Thank you very much.